In the ongoing quest to uncover the existence of extraterrestrial life, James Webb has ushered in a new era of discovery. It was designed to observe the universe in infrared wavelengths, allowing scientists to study the cosmos in ways previously unimaginable. And now, in a recent remarkable revelation, James Webb has provided scientists with exciting new insights into the conditions on Proxima b, a prime candidate for the search for life, fueling optimism that this planet might have the potential to harbor life. Proxima b was discovered in 2016 by astronomers using data from the European Southern Observatory's HARPS spectrograph. The planet orbits Proxima Centauri, a red dwarf star that is much cooler and smaller than our Sun. Proxima b is roughly the size of Earth, and it resides in the star's habitable zone, also known as the Goldilocks zone. This zone is the region around a star where conditions might be just right for liquid water to exist on the surface of a planet, an essential ingredient for life as we know it. However, Proxima b is not without its challenges. The planet is tidally locked to its star, meaning one side always faces Proxima Centauri while the other remains in permanent darkness. This could lead to extreme temperature differences between the day and night sides of the planet, complicating the potential for life. Additionally, Proxima Centauri is known to be a flare star, periodically emitting intense bursts of radiation. Such radiation could strip away a planet's atmosphere or make it inhospitable to life. Despite these challenges, Proxima b's proximity to Earth, combined with its location in the habitable zone, makes it a prime candidate for the search for extraterrestrial life. Things just got more exciting when most recently, the James Webb Space Telescope has provided an array of new stunning data on Proxima b, offering intriguing insights into the planet's atmosphere and the possibility of life. One of the most significant aspects of James Webb's observations is the data it has provided on the composition of Proxima b's atmosphere. Using its powerful spectroscopic instruments, the telescope has detected the presence of several key molecules in the planet's atmosphere, some of which are associated with the potential for life. Early data suggests that Proxima b's atmosphere may contain a mixture of carbon dioxide, water vapor, and methane. These molecules are particularly important in the search for life because they are key ingredients in the biochemical processes that sustain life on Earth. The presence of methane, in particular, is intriguing because it is a gas that, on Earth, is produced primarily by biological processes, such as those carried out by microbes in the guts of animals or in wetlands. While methane can also be produced through geological processes, the fact that it is present alongside other potential biomarkers raises the possibility that Proxima b could harbor some form of life. The detection of water vapor in the atmosphere is also significant. Water is essential for life as we know it, and its presence in the atmosphere of Proxima b suggests that the planet may have liquid water on its surface. While the existence of liquid water is not guaranteed, it is a promising sign that Proxima b could support the necessary conditions for life to exist. Another key aspect of Proxima b's potential habitability is its climate. As told, as a tidally locked planet, one side of Proxima b is perpetually exposed to its star, while the other side remains in constant darkness. This could lead to extreme temperature differences between the two hemispheres, with the day side experiencing scorching heat and the night side remaining frozen. Such temperature extremes could make it difficult for life to thrive. The Webb telescope has provided new insights into the planet's temperature distribution. Using its infrared imaging capabilities, the telescope has been able to map the temperature variations across Proxima b's surface. Early results suggest that there may be significant heat redistribution from the day side to the night side, possibly due to the presence of an atmosphere capable of carrying heat around the planet. This would reduce the extreme temperature differences between the two hemispheres, making the planet more hospitable to life. Additionally, Webb's data suggests that the planet's temperature is relatively moderate overall, with the day side being hot but not excessively so. This could mean that Proxima b's habitable zone if it exists, might be more expansive than initially thought. If an atmosphere capable of retaining heat exists, the planet's surface temperature could remain within a range that supports liquid water, especially in regions near the planet's twilight zone where day and night meet. A new chapter in the exploration of Proxima b was written when James Webb made an unprecedented discovery: city lights shining on the surface of Proxima b. This discovery, put simply, is nothing short of astonishing. For the first time, astronomers may have detected artificial light on a distant exoplanet. While the concept of city lights is familiar to us here on Earth, the notion that such illumination could exist on another planet raises profound questions about the potential for intelligent life elsewhere in the universe. This breakthrough was made possible by James Webb's highly sensitive infrared instruments, which allow it to detect faint signals from distant worlds. While the telescope has been primarily used to study the chemical composition of exoplanetary atmospheres and search for biosignatures, its advanced technology is also capable of detecting unusual sources of light on planetary surfaces. In this case, the team studying Proxima b's atmosphere noticed an anomalous increase in infrared light emissions coming from the planet's night side. At first, the researchers were puzzled. Natural processes such as volcanic activity or reflected starlight could potentially explain the increased light levels. However, after extensive analysis, the team concluded that the light patterns observed were not consistent with any known natural phenomena. The intensity and distribution of the light matched what one would expect from the artificial lighting of a city, specifically, patterns resembling the arrangement of streets and urban areas. This led to the hypothesis that the light emissions could be the result of artificial activity, possibly from an intelligent civilization. Although the evidence is far from conclusive, and alternative explanations remain possible, the discovery would mark a major milestone in our understanding of life in the cosmos. The most obvious and exciting implication of finding city lights on Proxima b would be the confirmation of extraterrestrial intelligence. After decades of searching for signs of life beyond Earth, humanity would finally have direct evidence that intelligent civilizations exist elsewhere in the universe. While scientists have long speculated about the existence of alien life, the detection of artificial lights would offer proof that such civilizations have not only evolved, but have also reached a technological level similar to, or perhaps more advanced than, our own. This discovery would fundamentally alter humanity's understanding of life, intelligence, and civilization. It would have profound philosophical and sociological implications for humanity. It would force us to confront the possibility that we are not alone in the universe, and that intelligent life has developed independently on other worlds. This could lead to a reevaluation of humanity's place in the cosmos and the value of our own civilization. The discovery could inspire new philosophical debates about the nature of consciousness, technology, and the ethics of interacting with extraterrestrial civilizations. It could also spark renewed interest in space exploration and interstellar communication. Not only that, the discovery of city lights on Proxima b would open a new frontier for the search for extraterrestrial intelligence. Either way, when it comes to the search for inhabited exoplanets, we have to be honest about the fact that our ignorance is tremendous. We don't know how frequently life arises in the universe, or where it's most likely to do so. We don't know how often that life survives and thrives over long periods of time, or how frequently it dies out very quickly. We don't know the probability of a world developing complex or even intelligent life, and we don't know whether the chemical reactions and processes that underlie life on Earth are common, rare, or even one of a kind on our planet. However, because the laws that govern the universe are the same everywhere, and the ingredients within each part of the universe can be measured, we believe we can identify which sets of conditions are likely to be the most conducive to life. In particular, the ideal candidate for discovering a potentially inhabited exoplanet should correspond to the following properties. It should be rocky, with a thin atmosphere, similar in size to Earth, but not much larger, around a star with a stable, continuous energy output, at a distance conducive to the presence of liquid water on its surface, with a similar abundance of heavy elements to our own solar system, where enough time has passed so that life has had a transformative impact on the planet's biosphere, and where it's close enough so that near-future technology could reveal those relevant key biosignatures. The first, and arguably the most important, constraint on life is that any potentially habitable world requires a suitable star. If your parent star is too massive, it will undergo stellar evolution too quickly, roasting any life on the planet within only a few 100 million years. Not enough time for anything interesting to arise. On the other hand, the most common type of star, the low-mass red dwarfs, require their planets to be in very close, tight orbits to receive an appreciable amount of stellar energy. But at those distances, these active, flaring stars would easily strip away any atmospheres. There must be a sweet spot in between the two extremes where long-term, stable, habitable conditions are likely. The second constraint, arguably one that's at least as important as the first, is on the nature of the planet in question itself. Although there's a large gap between the properties of a planet that's the mass size of something like Venus or Earth and the mass size of something like Uranus or Neptune, only a planet with an accessible solid surface and a thin gaseous atmosphere are of interest for life forms, similar to those found on our own planet. As a result, Mercury-sized planets are probably too small, but you can only be about 25–30% larger than Earth and about twice as massive before your atmosphere becomes too thick for Earth-like life. Although more than 5,000 exoplanets have now been identified, confirmed, and characterized, very few of them actually make for good candidates for life according to these criteria. Most of the exoplanets that have been found are quite a fair amount larger than Earth, and are likely to have a substantial volatile envelope of gases surrounding them, disfavoring the potential for surface life. Most of the Earth-sized exoplanets we know of are hot, very close to their parent stars and well inside any reasonable definition of a habitable zone. And most of the Earth-sized exoplanets that are found within their stars' habitable zones are found around the lowest mass stars of all, tiny red dwarf stars that tend to flare copiously, making the survival of an orbiting planet's atmosphere unlikely. Most of the exoplanets touted as the likely ones to harbor life, including Proxima Centauri b and the planets orbiting the TRAPPIST-1 system, are found around actively flaring red dwarfs that are quite likely to strip the atmospheres off of any surrounding worlds in short order. It's precisely this combination of factors that makes the TOI 700 system such a compelling, interesting one. Although TOI 700 is an M-class star, a red dwarf, it's one of the more massive red dwarfs out there, with more than 40% the mass of the Sun. As it only slowly rotates, completing a full 360-degree turn once every 54 days, even slower than the Sun, its activity level is quite low. Consistent with slow rotators, it has never been seen to flare, has negligible sunspot activity, and indicates that the star has been around for a while, at least 1.5 billion years already. Additionally, it has almost an identical heavy element content to our Sun. TOI 700 was initially, from the TESS mission, discovered to have 3 planets around it, is now known to possess at least 4, with 2 of them potentially inhabited. Its known planets are TOI 700b, with an orbital period of 10 days and a size that's 91.4% as large as Earth, TOI 700c, with an orbital period of 16 days and a size that's 2.6 times as large as Earth, TOI 700e, the new planet, with a period of 28 days, and that's 95% the size of Earth, and TOI 700d, the first Earth-sized planet found in the habitable zone of a stellar system by TESS, with a period of 37 days and a size that's 105% of Earth's. While TOI 700c is likely some sort of mini Neptune, the other 3 planets are almost certainly rocky. Interestingly, now that a fourth planet has been discovered, it appears these planets orbit in a series of resonances. In particular, TOI 700b completes 8 full revolutions for every 5 full revolutions completed by TOI 700c. TOI 700c completes 7 full revolutions for every 4 revolutions by TOI 700e. And TOI 700e completes 4 revolutions every time TOI 700d completes 3 revolutions. With the limited amount of quality observing time that TESS spends on an individual target such as this, it's important to recognize that there are likely more worlds exterior to TOI 700d that remain to be discovered, and that more observing time will be key to uncovering them. Importantly, around every star, there should be a region that we call the habitable zone, where, if the planet were to have a similar atmosphere and composition to Earth, it would have liquid water on its surface at its present distance from its parent star. There's also the extended or optimistic habitable zone, where somewhat tinkering with the planet's atmospheric properties could still admit surface liquid water under the right conditions. When you apply that set of conditions to the TOI 700 system, you find that the inner 2 planets, TOI 700b and TOI 700c, are far too hot to be of interest for any sort of biological activity, with TOI 700c also facing the issue of likely not being a rocky planet. However, TOI 700e and TOI 700d are almost certainly rocky in nature, with the innermost planet being found in the optimistic habitable zone, and the outermost planet located in the normal habitable zone. Both of these planets, even if tidally locked to their star, might still be excellent candidates for hosting life and being actually inhabited. There's also the suggestion, compelling because of how much farther out than the orbit of TOI 700d the habitable zone of the parent star extends, that perhaps there's another planet, perhaps also rocky, that exists maybe smack in the middle of TOI 700's habitable zone. With more test data and the opportunity to detect less frequent but still periodic transits on the way, we might have as many as 3 or even 4 candidate worlds that could be home to life. There are a lot of worries about whether life is even possible around an M-class red dwarf star, however, that are not necessarily so easy to dismiss. These red dwarfs, overall, are pretty much guaranteed to tidally lock their orbiting planets to themselves, so that one side always faces their parent star and the opposite side always faces away. On average, they emit very little ultraviolet radiation, and most of their energy is in infrared light, but with bursts of X-rays and lots of flares. It's often why people talk about stars that are sun-like. The K-class, slightly less massive than the Sun, G-class, which includes the Sun, and F-class, slightly more massive than the Sun, as ideal candidates for inhabited planets. But this is only a general thought, not a hard and fast rule. TOI 700 is very interesting for a red dwarf star, because much like 2 of Kepler's stars of interest, Kepler 186 and Kepler 438, both of which also possess potentially rocky habitable planets, it's very close to the border between K-class and M-class stars. If these stars don't flare and don't strip their orbiting planets' atmospheres away from them, they might be relatively ideal locations for life to arise and thrive for extremely long periods of time. Importantly, there's a lot of new data coming on this system. TESS is about to enter a period where it will survey the region of sky containing this star and its system of planets, collecting more data that might potentially reveal additional, outermost planets. There has been a substantial amount of observing time awarded to use the espresso instrument aboard the ESO's Very Large Telescope to track how the motion of the parent star, TOI 700, changes over time, which should do an excellent job of revealing the planetary masses of the planets present in this system, particularly the innermost ones. And there's also data coming about the ultraviolet spectrum of the star, which could lead to conclusions about the likely atmospheric behaviors and properties found on the orbiting planets. Although the planets are all likely tidally locked, there are still viable scenarios where these worlds are habitable. If the atmosphere is rich in carbon dioxide, the world will be uniformly hot, with planet-encircling winds upon it. Although life is disfavored, a wet, ocean-covered world with those properties might still allow habitability. But a cloudless, oceanless world with an Earth-like atmosphere would possess winds directed from the night side to the day side, with a ring of potential habitability on the day-night boundary. With upcoming measurements, we might be able to draw inferences about the potential habitability of the surrounding worlds. There are only a scant few planetary systems that are truly excellent candidates for having inhabited worlds around them, and the TOI 700 system is, by many metrics, a contender for the most likely system known today to be home to biological activity around it. It's been around for more than 1.5 billion years, more than enough time for biological activity to transform the thin region where the planet's surface meets its atmosphere into a rich biosphere, with the potential to trigger planet-wide changes to their own atmospheres. If life were to transform the composition of such a world's atmospheric contents, we could potentially detect it with a future observatory, such as the upcoming Habitable Worlds Observatory or, alternatively, the proposed LUVOIR mission. Although we have yet to find our first instance of an inhabited planet beyond planet Earth, it's something that's not only within the reach of 21st century technology, it's something that we're closing in on, little by little, with each subsequent observation. That's why scientists can't give up the hunt for alien life. After all, within our observable universe, since the dawn of the hot Big Bang, sextillions of stars have formed. Of those, the majority of them are found in large, massive, rich galaxies. Galaxies comparable in size and mass to the Milky Way or greater. By the time billions of years have gone by, most of the new stars will have sufficiently large fractions of heavy elements to lead to the formation of rocky planets and molecules that are known as precursors to life. These precursor molecules have been found everywhere, from comets and asteroids to the interstellar medium to stellar outflows to planet-forming disks. And, at this critical step, we find ourselves face to face with the end of our scientific certainty. Where and under what conditions does life come into existence? On those worlds where life arises, how frequently does it survive and thrive, persisting for billions of years? How often does that life saturate its habitable regions, transforming and feeding back on its biosphere? Where this occurs, how often does life diversify, becoming complex and differentiated? And where that occurs, how frequently does life become intelligent enough to become technologically advanced, capable of communicating across or even traversing the vast interstellar distances? These questions aren't merely there for us to philosophically ponder. They're there for us to gather information about, and eventually, to draw scientifically valid conclusions about such probabilities. Of course, there are plenty of valid explanations for why we haven't succeeded in our searches for life just yet. The most sobering and the most pessimistic is that it's possible that one or more of the steps required to give rise to the type of life we'd be sensitive to are particularly difficult, and only rarely can the universe achieve them. In other words, it's possible that any one of life, sustained life, complex and differentiated life, or intelligent and technologically advanced life are rare, and none of the worlds we've surveyed possess them. That's a possibility we have to keep in mind so long as we're committed to remaining intellectually honest. But there's no reason, at least so far, to suspect that's the primary reason we haven't discovered life beyond Earth just yet. The old saying, if at first you don't succeed, try again, applies wherever the odds of success are unknown. But we have every indication that success is possible under the right circumstances. Here on Earth, the evidence strongly indicates that our home planet is an example of such circumstances. And hence, it's likely that there are places all throughout space and time where life sustains itself, evolves to become complex and differentiated, and achieves a level of technological advancement sufficient for interstellar communication. The big unknowns are in the probabilities of the various types of alien life that are actually out there, not in the question of whether such achievements are possible within our universe. That doesn't mean that we should take seriously every claim that's been made, even by scientists, that alien life has been found. The WOW signal, for example, was a high-powered radio signal received over the span of 72 seconds back in 1977. Although its nature is unknown, it has never been replicated, either back at the original source or anywhere else. Without confirmation or repeatability, we can draw no affirmative, definitive conclusions. Fast radio bursts, like many signatures observed astronomically, appear in many locations both in and out of our galaxy, but have no indication that they were intelligently created. They are likely simply a natural astronomical phenomena whose origins have yet to be determined. NASA's Mars Viking lander conducted numerous tests for life on the Martian surface, with one experiment, the labeled release experiment, giving a positive signature. However, the possibility of contamination, the lack of reproducibility, and the lack of a verified follow-up experiment has cast tremendous doubt on the biological positive interpretation of the experiment. And despite the possibility of encountering interstellar space probes, direct alien contact, or even the ubiquity of alien abduction stories, no robust verification of any of these claims has ever come forth. We have to keep our minds open while at the same time remaining skeptical of any grand claims. The conclusions we draw can only be as strong as the supporting evidence for them. It's primarily for these reasons. We have every indication that the universe has all the necessary ingredients for life, but no indication that we've found it just yet. That it's so vital to keep looking in a scientifically scrupulous way. When we do announce that we've found extraterrestrial life, we don't want it to be another instance of crying wolf with insufficient evidence that we've found a wolf. We want the claim to be supported by overwhelming, unassailable evidence. That means building fleets of orbiters, landers, sample return missions, and laboratory-equipped rovers to explore a wide variety of worlds in our solar system. Venus's atmosphere, Mars's surface, Titan's lakes, and the oceans of Europa, Enceladus, Triton, and Pluto, among others. That means building superior coronagraphs on world-class space-based and ground-based telescopes, considering the construction of a starshade and investing in transit spectroscopy. By imaging the atmospheres and surfaces of exoplanets, including breaking down their molecular and atomic constituents and abundances over time, we should be able to identify any world with a life-saturated biosphere. And that means continuing to search with greater precisions and sensitivities across the electromagnetic spectrum for any signals that might come from an intelligent species seeking to communicate or announce their presence. If you don't find fruit on the lowest hanging branches, that doesn't necessarily mean you give up on the tree. It means you find a way to climb higher, where the fruit may be present, but out of your present reach. This might also include expanding our searches for extraterrestrial intelligence. While most searches focus on far-reaching radio transmissions, it's possible that alien civilizations who seek to communicate across the stars and galaxies will rely on a different technology. Perhaps we should be monitoring the tails of water masser lines or the 21 cm spin-flip transition of hydrogen. Perhaps we should be looking for patterns in pulsar signals, including correlating signals between pulsars. Perhaps we should even be looking for extraterrestrial intelligences in gravitational wave signals that we have yet to discover. Wherever a signal can be encoded by a sufficiently advanced species, humanity should be looking and listening. There are also avenues to explore that won't reveal alien life, but could help us understand how it arose and arises throughout the universe. We can recreate the atmospheric conditions found on other worlds, or even as they were on Earth long ago in the lab, with an eye toward recreating the origin of life from non-life. We can continue exploring the possibility of having nucleic acids co-evolve with peptides in an early prebiotic environment. perhaps the most compelling candidate for how life first arose on Earth. The rewards of finding out that we're not alone in the universe would be immeasurable. Perhaps we could learn how to survive the great environmental threats that face us: hazardous asteroids, a changing climate, or violent space weather events. Perhaps there are even more important lessons to be learned about how to overcome our own insufficiencies as human beings. The great challenge of moving beyond our primal nature. Perhaps other civilizations have success stories to offer us, recounting how, in the early days of their technological infancy, they overcame such issues as overconsumption, where they devoured their planet's resources beyond the point of sustainability, short-term thinking, where they addressed the immediate, urgent problems at the expense of long-term ones that threatened their existence, or the emergence of disease, famine, pestilence, and ecological collapse, resulting from the global changes wrought by a post-industrial society. Our impulses toward greed, plunder, and self-gratification may not be unique, and there may be more experienced, wiser species out there that have figured out solutions that elude us today. Perhaps, if we're lucky, they may have lessons waiting in the wings for us that could guide us toward a more successful future. Many of us can imagine two different futures unfolding for the enterprise of human civilization. There's the one we should strive to avoid, where we resort to infighting, squabbling over the limited resources of our world, descending into ideologically driven wars, and ensuring our own eventual destruction. If we never find life beyond Earth, never find anyone else to communicate with, exchange information and culture with, and to give us hope that there's a future for humanity out there among the stars, perhaps extinction will indeed be our most likely outcome. But there's another possible outcome for humanity, a future where we come together collectively to face the gargantuan challenges facing humans, the environment, planet Earth, and our long-term future. Perhaps the discovery of life beyond Earth, and potentially of one or more intelligent, spacefaring, extraterrestrial civilizations, might give us not only the guidance and knowledge we need to survive our growing pains, but something far grander than any terrestrial achievements to hope for. Until that day arrives, we must make do with the knowledge that, at present, we have only one another to extend our kindnesses and compassion to. Playing with numbers in Drake's equation has showed us that intelligent life forms may be few and far between. The nearest civilization may be thousands of light years away, if we are lucky. Finding a candidate among our closest neighbors must be considered extremely unlikely. But don't you know that there is an Earth-like planet in our neighborhood, located just 4 light years away? It's Proxima b. 8 years ago, the whole world of science news was recently abuzz with discovering the closest alien planet to our solar system. While the detection seemed solid, more confirmation is always good. And now the James Webb Space Telescope has provided that extra and more detailed confirmation. In an extraordinary observation, the Webb Telescope has just announced the clearest image of Proxima b in history, revealing an astonishing discovery that could change everything we know about the universe and life on Earth. Join us as we dig deep into the mysteries of Proxima b and discover whether it could be the next Earth. As shocking as it sounds, we find exoplanets, or planets orbiting stars other than our Sun, all the time now. We know of nearly 6,000 such planets, plus another 10,000 planet candidates. So what makes Proxima b so particularly exciting? First off, Proxima Centauri b is of particular interest since it's orbiting the closest star to our Sun, only 4.2 light-years away. Its confirmation underscores current findings that such worlds are common in our galaxy. Proxima Centauri b is very similar in size to Earth, with a mass of 1.17 Earth masses. It orbits its star in only 11.2 days, in contrast to our Earth's year-long orbit around our Sun. That means Proxima Centauri b is a lot closer to its star than Earth is to the Sun. But Because the star is a red dwarf, much smaller and cooler than our Sun, its orbit is indeed within the habitable zone of Proxima Centauri. Interestingly, Proxima Centauri b receives about the same amount of solar energy from its star that Earth does from our Sun. So, theoretically, Proxima Centauri b could have water on its surface. It could be habitable, but, of course, we don't yet know all the details about habitability for exoworlds. We do know that many factors affect a planet's habitability, such as temperature, composition of the planet and atmosphere, water, and radiation from its sun. Red dwarfs like Proxima Centauri are known to emit flares, and these flares make habitability for red dwarf exoplanets even more complex and interesting. Worse, our usual methods for detecting biosignatures won't work with Proxima Centauri b. Most exoplanets are discovered through the transit method, where a planet regularly passes in front of its star from our point of view. We see the recurring dip in a star's brightness, and we know the planet is there. For transiting exoplanets, we can look for changes in the spectrum of the star as the planet transits. Some of the starlight passes through an exoplanet's atmosphere, and some wavelengths get absorbed by the atmosphere. By looking at the pattern of absorption, we can fingerprint different molecules. This is how we've detected the presence of water, carbon dioxide, and other molecules in exoplanet atmospheres. But Proxima Centauri b isn't a transiting planet. It was discovered by a different method known as Doppler spectroscopy. When we look at the light from Proxima Centauri, we can see its spectrum redshift and blue shift slightly over time. The gravitational pull of Proxima Centauri b makes the star wobble slightly. So we know the exoplanet is there and have a good idea of its size and mass. But since it doesn't transit its star, we can't observe its atmospheric absorption spectrum. Fortunately, there is another way we might find life. From space, the most obvious sign somebody lives on Earth is the glow from the night side of our planet. Our cities emit light that's shed into the cosmos. The lights could be seen by telescopes on distant worlds if they truly exist, and vice versa. We Aslo could tell alien technology exists on another planet in the similar way. In principle, the idea is simple. Rather than looking for light passing directly through the atmosphere, look instead for light that has reflected off the planet directly. We've done this for planets such as Mars and the outer planets, which don't transit the sun, so we could do it for exoplanets as well. For example, we may be able to see the light of a distant world waver with the transit of a massive constellation of satellites. Atmospheric pollution may be detectable from nuclear conflict. But while these indications of technology could also be caused by natural phenomenon like orbiting debris or a comet impact, artificial illumination is distinct from the natural light of stars. The problem is that reflected starlight from a planet is tiny compared to the radiance of the star itself. Detecting the reflected light of a planet is like capturing the light of a firefly flittering near the edge of a spotlight. Luckily, we are living in the golden age of astronomy. Today, we have a new generation of telescopes that are powerful enough to see lights on distant worlds. One of them is the James Webb Space Telescope. Scientists scaled artificial illumination as a fraction of the solar illumination, reflecting from the day side of the planet. 0% on this scale would assume that the night side of the planet is completely dark, devoid of artificial illumination. 100% means the night side of the planet is as equally bright as the day side. The type of light used by the hypothetical civilization on Proxima b is assumed to be similar to LEDs on Earth, which have a distinct artificial spectrum. The results? If the artificial night-side illumination of Proxima b reaches 5% of the natural day-side illumination, James Webb could detect the artificial light with 85% certainty. And if artificial illumination were to reach 9%, the Webb telescope detection confidence would rise to 95%. But James Webb turned out to be much better than we anticipated. Webb's mirrors collect light from the sky and direct it to the science instruments. The instruments filter the light or spectroscopically disperse it before finally focusing it onto the detectors. Each instrument has its own detectors. The detectors are where photons are absorbed and ultimately converted into the electronic voltages that we can measure. Webb needs extraordinarily sensitive detectors to record the feeble light from faraway galaxies, stars, and planets. It needs large area arrays of detectors to efficiently survey the sky. Webb has extended the state-of-the-art for infrared detectors by producing arrays that are lower noise, larger format, and longer lasting than their predecessors. Thus, in a recent observation, James Webb has focused its sharp eyes on the closest alien planet to our solar system. New insights obtained from James Webb have dramatically increased the amount of data on exoplanets and their atmospheres available to researchers. We all know that Proxima b, like our planet in several ways. But there are many ways we know that it must differ from our planet Earth, including it must be tidally locked to its star, where the same face always faces the star and the same face always faces away. It will have 3 climate zones, an ultra-hot one where it's always sunny, an ultra-cold one where it's always night, and an on-the-border one where it's always sunset, sunrise, and the solar flares coming from the star will potentially be a danger for stripping the atmosphere away. Of course, we can concoct scenarios where the planet hangs onto or replenishes its atmosphere and has conditions conducive to life. But this is nothing more than wishful thinking. In reality, we do not even know whether this planet is Earth-like or Neptune-like. The typical border between an Earth-like world, where you have a rocky surface with a thin atmosphere, and a Neptune-like world, where you have a large gas envelope surrounding your world, is about 2 Earth masses. Proxima b has a minimum mass of about 1.3 Earths, but that's if the alignment is perfectly edge-on. Since there's no transit, we know the alignment cannot be exactly perfect, but how imperfect is it? That's gloriously unknown. If the alignment is inclined at more than about 25 degrees from our line of sight, it's likely to be a gaseous world, not a rocky, Earth-like one. But at this point, without further information, we cannot know. If we were going to be as accurate as possible, we would state that there is a planet with an orbital period of 11.2 days, orbiting the closest star to us, Proxima Centauri. It receives 65% of the solar energy that Earth receives, and has a minimum mass of 130% the mass of Earth. That's it. That's all we know for certain. If we wanted to speculate, we could discuss all the reasons Proxima b is likely to be inhospitable to life, what challenges this planet faces if it wants to achieve habitability, and what we'd have to measure to know for sure. But the truth is that we don't know any more than this. Until we have better, more comprehensive data on this world, all we know is its period, the energy it receives, and its minimum mass. The age of exoplanet astronomy is upon us, and although the search for city lights on habitable planets may sound speculative, it is worth pursuing as a potential techno-signature with planned instruments. It is possible James Webb will detect far less illumination or see the same on much more distant exoplanets. Proxima b orbits its star every 11.2 days, providing 32.6 more opportunities for its possible inhabitants to celebrate their birthdays than we have on Earth, once per 365.2 days. The high demand for bright lights during birthday parties on the night side of Proxima b would be a reason for us to celebrate as well, if the signal was noticed by future telescopes. Once signs of life are found, sending a probe on Proxima is needed. But of course, a lot of technical challenges need to be overcome before we can hope to mount such a mission. In addition, a lot of questions need to be answered. For example, what kind of ship should we send to Proxima b or other nearby exoplanets? How long would it take for us to travel to it? The vast distance that separates us from Proxima b is terrifying. Compared to other regions of the cosmos, Proxima is almost in our backyard. but it would take approximately 78,000 years to go there with present technology, a calculation based on the maximum speed attained by our fastest probe, New Horizons, which was 59,000 kilometers per hour. If we wanted to reach Proxima in a reasonable 20 years, a spacecraft would have to travel at an average speed of more than 300 million kilometers per hour, which is about 28% of the speed of light. Regardless of this challenge, humans always strive to one day reach out and touch the stars. And it appears that even NASA has decided to visit there before the end of this century, with a project that is facing stiff opposition in some scientific circles, but which the American Space Agency believes it can launch by 2069. A date that is definitely not coincidental, as it recalls an event that occurred exactly 100 years earlier. That would certainly be a thrilling feat. To fulfill this dream, NASA will need a speedier method and more efficient technology to reach at least the nearest stars. Reaching the Alpha Centauri system in an acceptable amount of time would necessitate the development of a propulsion technology capable of at least 10% of the speed of light. The greatest challenge is storing the sufficient fuel load to enable the spaceship to accelerate steadily to the desired speed threshold. In spite of the seemingly insurmountable obstacles, numerous interplanetary spacecraft designs have been presented during the past few decades. In the 1960s, research and tests were done in the United States as part of the Orion project. The basic concept was to use the shockwave produced by the consecutive detonation of numerous tiny nuclear bombs to propel a spacecraft at high speed. Someone understood the project's potential for interstellar travel as well. Originally, the project was intended to transport massive masses into orbit or permit human journeys to Mars, but someone recognized its potential for interstellar travel. In the initial design, the Orion intended to rapidly release nuclear fission bombs, which, when detonated directly behind the vehicle, would give it a large boost via the impact of the shockwave formed on a unique shield capable of absorbing the shock without harm. Nevertheless, this notion, which would alleviate a number of the aforementioned issues, remains speculative and may be used to launch small probes to the stars. During the same time period, American physicist Robert Bussard presented an innovative solution to the mass problem by omitting the need for propellant. Thus was created the concept of the interstellar ramjet, a vehicle capable of gathering the hydrogen present between the stars and utilizing it to power a nuclear fusion engine. The collection of interstellar hydrogen would not be simple, in addition to the challenges posed by the construction of the engine. In fact, assuming an average density of 1 atom per cubic centimeter, to gather 1 kilogram of hydrogen at 1/10 the speed of light would require a funnel with a mouth of 5,000 kilometers in diameter, and the collected stuff would still be minimal in comparison to the requirements for propulsion. Interstellar ramjets, in all of its proposed forms, are therefore not regarded physically possible. In the 1970s, the British Interplanetary Society, led by British aerospace engineer Alan Bond, did a comprehensive study of the Daedalus variant of the Orion concept, possibly the most realistic interstellar ship design ever envisioned. Instead of nuclear weapons, the Daedalus was designed to utilize a succession of micro-explosions generated by the nuclear fusion of miniature deuterium and helium-3 tablets. The two-stage, fully autonomous spaceship may have reached 0.1 constant, or 10% of the speed of light, with a launch mass of 50,000 tons, 93% of which was propellant. This would have allowed it to reach Proxima in slightly more than 30 years, then broadcast the data obtained during the flyby back to Earth. However, very innovative solutions are required to handle the issues of energy consumption and journey time. Since its conception in the first half of the 1980s, the interstellar sail concept has undergone a number of revisions and enhancements, mostly to reduce the energy requirements of the journey and make its operation more realistic. In any case, The main parts of the system would be a very powerful laser or microwave transmitter, which would probably be in space, a giant lens that would focus the radiation into a very narrow beam, even from a long way away, and the interstellar sail itself, which would be able to catch the radiation and speed up a lot because of the pressure it created. And by sail, we do not mean a racing spinnaker, but something more like anything, at least 6 kilometers in diameter and just 30 grams in weight. Accelerated to 0.2 constant in only 2 weeks, Star-Wisp might reach the Alpha Centauri system within 21 years. Antimatter propulsion is another conceivable method. We know that when 1 gram of antimatter is turned into energy, it produces an enormous amount, around 70 times the energy produced by nuclear fusion and 4 billion times the energy produced by burning oil. Such an engine would enable us to reach approximately 40% of the speed of light, reducing the time required to reach Alpha Centauri to less than a decade. However, antimatter is currently scarce in nature and difficult to capture. Therefore, it is necessary to manufacture it, which is carried out in minuscule amounts in huge particle accelerators. Making engines for space exploration would take many kilos of it, however. This appears to be a negligible amount, yet it is significantly higher than what has been synthesized to date. Consider that it would take 1 billion years for an accelerator's antimatter factory to manufacture a single gram of antimatter. The conventional energy necessary to manufacture a few kilos of antiprotons every year corresponds to a total energy consumption of around 50 billion watts, which is equivalent to the power output of all nuclear power facilities in the United States. Currently, this is our scenario. We wish to visit the planet Proxima b, but we do not yet know how. Our technology is essentially still in its infancy, despite its tremendous development. No one can foresee what the human race will be able to accomplish by the fatal year 2069. But if growth continues at the current rate, along with many new issues to be solved, we will have vastly improved our abilities in precisely those fields essential to interstellar travel. Initially, expeditions to the stars will likely be done by intelligent robotic probes capable of moving at 0.1 constant and shrunk beyond currently imaginable limitations. As proposed by physicist Frank J. Tipler and described in Arthur C. Clarke's engrossing novel, The Songs of the Far Earth, even with simple probes such as these, humans could rapidly propagate throughout the galaxy as a result of the extraordinary progress being made in the fields of biotechnology, genetic and molecular engineering, embryonic development, and cell physiology. In practice, this would involve the creation of so-called von Neumann probes, that is, intelligent automatons that, upon arrival at their destination, would be able to construct copies of themselves and habitats for eventual living beings, including humans, synthesized in situ from the genetic code and instructions for the generation and development of embryos. After initiating the successful colonization of a planet, von Neumann's probes might construct new interstellar spaceships and automatons that would go to other star systems to repeat the feat. Obviously, we are discussing little probes and seemingly science fiction at that. But NASA will have to take into account the fact that interstellar flight with humans on board will involve mass and energy scales thousands to millions of times larger. Current understanding leads us back to the concept of interstellar arcs, which are massive, environmentally self-sustaining dwellings capable of traversing the stars for thousands of years, while numerous generations of humans, animals, and plants follow within them. These arcs might be modeled after the massive space colonies studied by physicist Gerald O'Neill in the 1970s and launched into interstellar space at speeds as low as 0.01 constant. It is impossible to conceive of the circumstances and motivations under which humans might embark on a voyage knowing that they would never reach their target. Probably only the gradual uninhabitability of our planet and other inhabited solar system planets might motivate people to make such an extreme choice. If it were possible to considerably lengthen human life or slow down metabolic processes during flight, and achieve at least 0.1 to 0.3 constant with the requisite big spaceships, the conversation would alter drastically. For this to become a reality, however, it will likely take several more centuries, unless physics continues to surprise us in extraordinary ways. How then will NASA fulfill its obligations? Could it have a card up its sleeve? We simply have to wait till 2069 to find out. In addition to observing Proxima b, scientists also expect James Webb to turn its eyes to other Earth-like planets. Discovering the first true alien Earth is a long-held dream of astronomers, and recent exoplanet discoveries have shown that small rocky worlds like our own are abundant in the galaxy. To qualify as potentially life-friendly, a planet must be relatively small and therefore rocky and orbit in the habitable or Goldilocks zone of its star, which is loosely defined as a location where water can exist in liquid form on a world's surface. When telescope technology improves, other factors will be considered as well, such as the planet's atmospheric composition and how active its parent star is. While Earth 2.0 remains elusive, here are 9 exoplanets regarded as the most Earth-like alien worlds discovered to date. 1. Gliese 667cc. Gliese 667cc lies just 22 light-years from Earth and is at least 4.5 times as massive as Earth. Gliese 667cc completes one orbit around its host star in a mere 28 days, but that star is a red dwarf considerably cooler than the Sun, so the exoplanet is thought to lie in the habitable zone. However, Gliese 667cc, which was discovered with the European Southern Observatory's 3.6-meter telescope in Chile, may orbit close enough in to be baked by flares from the red dwarf. 2. Kepler 22b. Kepler 22b lies 600 light-years away. It was the first Kepler planet found in the habitable zone of its parent star, but the world is considerably larger than Earth, about 2.4 times our planet's size. It's unclear if this super-Earth planet is rocky, liquid, or gaseous. Kepler 22b's orbit of 290 days is pretty similar to Earth's 365. The exoplanet orbits a G-class star like our Sun, but this star is smaller and colder than Earth's. 3. Kepler 69c. Kepler 69c, which is about 2,700 light-years away, is about 70% larger than Earth. So once again, researchers are unsure about its composition. The planet completes one orbit every 242 days, making its position within its solar system comparable to that of Venus within ours. However, Kepler 69c's host star is about 80% as luminous as the Sun, so the planet appears to be in the habitable zone. 4. Kepler 62f. This planet is about 40% larger than Earth and orbits a star much cooler than our Sun, according to NASA. Its 26-day orbit, however, puts Kepler 62f squarely within the habitable zone. While Kepler 62 orbits closer to its red dwarf star than Earth does to the Sun, the star produces much less light. Kepler 62f lies about 1 in 200 light-years away, and, due to its large size, is within the range of potentially rocky planets that may hold oceans. 5. Kepler 186f. This planet is at most 10% larger than Earth, and it also appears to reside in the habitable zone of its star, though on the zone's outer edge. Kepler 186f receives just 1/3 of the energy from its star that Earth gets from the Sun. Kepler 186f's parent star is a red dwarf, so the alien world is not a true Earth twin. The planet lies about 500 light-years from Earth. 6. Kepler 442b. Kepler 442b is 33% larger than Earth and completes an orbit of its star every 112 days. The discovery of Kepler 442, situated 1,194 light-years away from Earth, was announced in 2015. One study, published in the monthly notices of the Royal Astronomical Society in 2021, found that this exoplanet may receive enough light to sustain a large biosphere. The researchers analyzed the likelihood of different planets being able to carry out photosynthesis, They found that Kepler 442b receives sufficient radiation from its star. 7. Kepler 452b. This world, whose discovery was announced in 2015, is the first near-Earth-size planet that orbits around a star the size of the Sun, according to NASA exoplanets. Kepler 452b is 60% larger than Earth, and its parent star is 10% larger than the Sun. Kepler 452 is very similar to our Sun, and the exoplanet orbits in the habitable zone. Its discoverers have said at 1.6 times the size of Earth, Kepler 452b has a better-than-even chance of being rocky. Kepler 452b resides 1/400 light-years from Earth. It takes Kepler 452b just 20 days longer to orbit its star than Earth does. 8. Kepler 1649c. When the data from NASA's Kepler Space Telescope was reanalyzed, scientists discovered Kepler 1649c. The exoplanet was found to be similar in size to Earth and orbiting in its star's habitable zone. During the initial data collection from the telescope, a computer algorithm misidentified the astronomical body, but in 2020, it was discovered to be a planet. Kepler 1649c is located 300 light-years from Earth and is only 1.06 times larger than it. When comparing the light that the two planets receive from their stars, scientists found that this exoplanet receives 75% of the light Earth does from the Sun. 9. TRAPPIST-1e. Orbiting the star. TRAPPIST-1 are the most Earth-sized planets ever discovered in the habitable zone of a single star. This planetary system is made up of 7 worlds. Water on most of these planets is likely to have evaporated early in the system's formation, Space.com previously reported. However, a 2018 study found that some of these planets could hold more water than Earth's oceans. One of the worlds, called TRAPPIST-1e, is thought to be the most likely to support life as we know it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.